All right, open up your book to section 9-6. We're on page 463 in your book. The title of this section is Vector Addition. The objective is given two vectors, add them to find the resultant vector. All right, a couple of terms that we need to understand here when we're working with vectors. We're going to be doing some vector addition, and in order to make that easiest, we're going to be breaking it down into its component form. So to do that, we use what's called a unit vector. We've talked about the unit circle. The unit circle is just a circle centered at the origin with a radius of 1. That's the reason we call it the unit circle, because it has a radius of 1. So when we use the term unit here for a unit vector, we're talking about a vector whose magnitude is 1. Notice that this doesn't say anything about its direction, just its magnitude. So a unit vector is a vector whose magnitude is just 1. We have two special vectors then that we're going to work with. A horizontal unit vector and a vertical unit vector. So these two vectors here will take a vector with a magnitude of 1 because they're a unit vector, but this gives them a direction now when we talk about a horizontal unit vector and a vertical unit vector. So this will define for us both a direction and a magnitude. All right, so the horizontal unit vector is a unit vector in the positive horizontal direction. And we denote that by the vector I with an arrow over top of it to indicate it's a vector. So the vector I with an arrow over top of it, that is a special vector for us. It's a unit vector that's in the positive horizontal direction. For our vertical unit vector, that's again a unit vector in the positive vertical direction. And this one will denote by vector J. So those two vectors will be vectors that we use here to rewrite any given vector into its horizontal and vertical components is what we want to be able to do. All right, so how exactly do we split that up? How do we take a vector and rewrite it in its horizontal and vertical component form? Well, here is the answer to that question. The vector components, that is the horizontal and vertical components of a vector. If you have a vector v, and it has a magnitude which is the absolute value of v, and a direction we'll call theta, and we're measuring this in standard position, then you can calculate the following, or you can name the vector in the following way here. We can say that vector v is equal to some coefficient, we'll call it x times vector I. It's actually a scalar quantity times vector I, plus some vertical coefficient. It's actually a scalar quantity times our unit vector, our unit vertical vector there, j. So you can take a vector and you can break it down into the sum of these two vectors, any vector. You can break it down into these two. And over there on the right, it kind of illustrates how you can do that. If I've got some vector v, regardless of what direction that vector has or what magnitude it has, I can always take that vector and draw in these horizontal and vertical vectors, multiply those unit vectors by the correct scalar quantity in order to get them the right magnitude there, so that the sum of those two vectors turns out to give me vector v. Realize that all we're looking at here is a vector sum. We're doing vector addition. And we're kind of breaking down vector v, thinking of it as a resultant vector, and coming up with the two components that add up to give us this vector v. I want one component to be horizontal and the other one to be vertical, though. So every vector we can break down this way. So how do you go about calculating what x and y are equal to? Well, it goes back to trig. We've done this many times there, that if I give you a triangle or if I give you a point in the coordinate plane and tell you it's the distance between that point and the origin, and I tell you the name of that point there, you can come up with the, or sorry, not the name of the point, but I tell you the angle between the positive x-axis and that line that goes between the origin and that point. You can come up with for me what the horizontal and vertical components are there. You can come up with the x and the y, or we call them u and v when we were first learning about this. So x turns out to be just the magnitude of your vector times the cosine of theta. You can check that out. If you take the cosine of theta, it's going to be the adjacent side divided by the hypotenuse. The adjacent side has a magnitude of just x, and the hypotenuse has a magnitude of the magnitude of v, the absolute value of v. Solve that for what x is equal to, and there you go. You got your equation. Do the same thing for y. Y is the magnitude of vector v times the sine of theta. Hopefully those are formulas that you recognize already from physics, that you've done some work with vectors in there, and you know how to write the horizontal and vertical components of a vector from that work as well. Now, you can also calculate the magnitude of this vector here if you know the x and the y part. So you just simply use Pythagorean theorem here, the square root of x squared plus y squared. Or if you want to find out what the direction of that vector is, if I know the x and the y, I can use arctangent to solve that. Of course, it's the tangent inverse of y over x plus 180n. And again, it depends on what quadrant this vector would be in as to what value of n you're going to pick there. If we're in the first or the fourth, we let n be 0. If we're in second or third, the n is going to be 1. That's the same story we've been talking about in determining what value of n to pick here. Think about the quadrant you're in. That tells you the right value of n to pick. So every single vector, we can take and rewrite it in this form as long as I know its magnitude and direction. And the nice thing about this is it makes doing some calculations with vectors much easier. So for every vector then, you can think of it this way. If you know the magnitude and direction of the vector, you can write that the vector is equal to this. It's the magnitude of your vector times the cosine of the direction times vector I, that horizontal unit vector I, plus the magnitude of your vector times the sine of the direction of your vector times that vertical unit vector j. All right, so we can take a vector and write it in this form as long as I know those two pieces. What's the magnitude? What's the direction? Let's try this out. Look at example 3 there on page 466. Example 3 says you have a vector. They call it vector A. It has a magnitude of 3 and a direction of 143 degrees. And the question is, they want you to resolve A into its horizontal and vertical components. They want you to write it in terms of I and J is another way of saying what they've asked you to do there. All right, so let's write down what they've given us here in this problem. They said that the magnitude of vector A is equal to 3. And they said the direction, I'm going to call it theta, is equal to 143 degrees. Okay, so those are the two pieces I need in order to write this in its component form. That was the last thing that we said on the previous slide. So vector A can be written as the magnitude of the vector, which is 3, times the cosine of the direction, which is 143 degrees, times your horizontal unit vector I. And we add to that the magnitude of the vector times the sine of the direction of that vector times your vertical unit vector j. There is that vector in its component form, your horizontal and vertical component form. Now, if you want to if you want to simplify this, if you want to actually calculate what those components are, you can grab your calculator and do that. So let's check that out. Grab your calculator and we'll do that. So our two components here on our vector, we've got 3 times the cosine of 143 degrees. 3 cosine of 143. Make sure you're in degree mode here. That's the horizontal component, 1.805. And then it's 3 times the, oops, I said cosine and then I did sine. Let me do that again here. 3 cosine of 143. That's the horizontal part. That's a negative 2.34396, looks like. And then 3 sine of 143. We already did that, but that's 1.805. Okay, so that right there is the components of our vector here. We'll write it in that form there. Many times it's nice to just leave it in the form that we already have, since those are nice numbers, but sometimes we're going to need decimal approximations for these, so we'll write it that way. So it was a negative 2.396 times vector I, and then 1.805 times vector j. Don't forget to put your unit vectors on there as well. It's not just the negative 2.3 plus the positive 1.8. Got to get the vectors in there as well. And in fact, if you wanted to, you could then sketch this vector. They told you that it was 143 degrees and that it was a magnitude of 3. So if we were to sketch this vector from standard position, 143 is in the second quadrant. This would be an angle of about 143 degrees. And we'll say that this has got a magnitude of 3. So the two numbers that we came up with here for the components of this, if we were to look for what's the name of that point right there at the head of that vector, that right there is the point negative 2.396, 1.805. That's what these two numbers here represent. When we talk about the horizontal and vertical components of that vector, we're finding actually the coordinate points of the head of that vector, assuming the tail is at the origin. All right, that's a little bit more than what they asked, but nonetheless, that gives us a pretty good understanding of the process as well as what exactly are we finding there when we put it into its component form. All right, let's take a look at another example. This one gets a little bit further into what we really want to be able to do with vectors. They give us a vector A that has a magnitude of 5 at 70 degrees. Magnitude B is 6 at 25 degrees. And they want us to find the resultant R. Okay, so I'm just going to go ahead and write down what these vectors are. We now should understand how to write a vector in its component form. So let's just write it that way. They told us the magnitude was 5. So it's 5 cosine of 70 degrees times vector I plus 5 times the sine of 70 degrees times vector j. So that's vector A. Do the same for vector B. Vector B was 6 at 25 degrees. So it's 6 cosine of 70, oops, not the same angle. 6 cosine of 25 degrees times vector I plus 6 sine of 25 degrees times vector j. All right, so they want us to find the resultant as the sum of two components. That's part A on this one. So for part A, we're going to literally add these two up. R is what they call this, is going to be A plus B. Now the nice thing about writing these in their component form is that I can easily add these vectors together because all I do is add the corresponding components. That is, I'm going to add my I parts together, and then I'm going to add the j parts together. Keep those separated that way, and that will tell me the resultant vector here. So that's all we're going to do. This is equal to, let's put the I parts together. I've got 5 cosine of 70 degrees plus the 6 cosine of 25 degrees. That's times vector I. And now do the j parts. It's 5 sine of 70 degrees plus the 6 sine of 25 degrees. And that's times vector j. And let's go ahead and plug that into our calculator and see what we end up with for the individual components of these two parts here. So let me just clear off the screen. I don't need that calculation there anymore. All right, so sum those up. We've got the 5 cosine of 70 degrees plus the 6 cosine of 25 degrees. And I'm going to need these calculations a little bit later on. So I'm going to go ahead and just store this as, let's store it as x. That's how we named it on the previous slide there. When we were defining this, we had the x and the y part. So I'll call this the x part of this, which is 7.148. And then do the same thing, but do the sine. So it's 5 sine of 70, 6 sine of 25, and I'm going to store this into y instead of x. And you get 7.234, right? And I'm going to go ahead and write these vectors in this form here, or this vector in this form. So we end up with, this is equal to It was 7.147 times, actually 148 if I round that right. You can truncate it, that's fine too, but I usually round. 148 times vector I plus 7.234 times vector j. So there is the resultant vector as the sum of these two components. Now for part B, they want us to find the magnitude and direction of this vector. So to find the magnitude and direction, well, that was the second part of that previous slide where we define these component forms. So for part B, once I have this vector here, I can find its magnitude pretty straightforward. I can just say the magnitude of that vector is going to be the square root of these two components here. So it's the 7.148 squared, 7.234 squared. Add those up, take the square root, and we got ourselves a magnitude for this vector. So let's grab our calculator and do that. Again, the nice thing about storing these to x and y is now I'm ready to just do this calculation here. I can just take the square root of x squared plus alpha y squared. And there we go, 10.170, I guess if we round that. It's 10.170. All right, and again, if there's units on this problem, then keep those in there. I don't think they gave us units here indicating what we were working with there, but that's the magnitude of the resultant vector, 10.170 units. All right, the other part of this is to find the direction of this. So again, to find the direction of this vector, I'm going to call it theta. That's the arctangent, but I'm going to jump to the next step there because it's the tangent inverse of this 7.234 over 7.148 plus 180n. And again, to find out your value of n, consider where this vector would be, the resultant vector. If I've got an x value of 7.1, y value of 7.2, that sounds like I'm in quadrant number 1. And in quadrant number 1, I can let n equal 0. Now let's go ahead and calculate that. And again, the nice thing about storing these as x and y on my calculator is now I can just simply take the tangent inverse of that y value and divide it by x. And again, I'm letting n be 0, so don't worry about adding on 180 times 0, but otherwise you'd have to add a 180 on there. So 45.344. In fact, let me just grab a screenshot of that. So we end up with 45, and we shouldn't be surprised it's close to 45 degrees because your horizontal and vertical components were almost the same, so that's close to a 45-degree angle, 45.344 degrees. All right, so there we go. There's the second part of that, the magnitude and direction of that vector. Notice how nice it is to add those two vectors together and then also find the magnitude of those two. All right, I'm not having to go through all the work like I saw in the first half of this using law of cosines to find these things. Just get the vectors in their component form. The addition of them makes it real easy, and finding the magnitude and direction of your resultant vector, it should be a little bit easier. All right. The last thing here for us to talk about is navigation bearings. We talked about those in the first half of this section, and I want to come back and revisit those and talk about them a little bit further here and how we deal with angles when we're measuring those using navigation bearings and how we do these same calculations. So here's what we're going to do. If we are given a problem where we're given navigation bearings, then we're going to do a conversion. We're going to convert the navigation bearing to an angle in standard position. So whatever that navigation bearing is, we're going to convert it over to an angle in standard position. The reason for doing that is because everything we know about our trig functions, sine, cosine, and tangent, and our other three reciprocal functions, all are based on working with angles in standard position. We have not done any work with angles that are not measured in standard position. Doesn't mean you can't evaluate those trig functions at angles that are not measured in standard position, but we definitely need to do some work with them before we understand exactly how those work. And we have not done that. So the easier thing, I think, to do is to get rid of the navigation bearing and get it over to a standard position, because we're going to use our trig functions in this process, and it'll make the calculation a lot easier for us, so I don't have to try to figure out what happens if I'm working with an angle in a different orientation. All right, so we'll name the navigation bearing theta sub b. So you can see over there on the right, we've got our north, south, west, and east markers there. And I've got a angle marked there, theta sub b, which would be my angle as a bearing, a navigation bearing, which means I'm starting at the positive y-axis, north, and I'm measuring clockwise so that it's positive there, so it's going to be between 0 and 360. So we'll name that theta sub b. And then we're going to name the angle in standard position theta sub s. So notice what we're going to do is we're going to remeasure that angle to that for that vector. Find the direction of that vector in standard position, theta sub s. One thing that's nice about that is it turns out that those two angles are actually complementary. That is, they sum up to 90 degrees. So if you just take 90 minus theta sub b, even if the navigation bearing is more than 90 degrees, this will still work. It turns out that 90 minus that navigation bearing will give you your angle in standard position. So by calculating the complementary angle there, we can easily come up with that. And then you're going to solve the problem in terms of theta sub s. So we've now talked about how you can work with vectors and use those to help us find magnitudes and directions. So solve the problem like as if they had given the problem in standard position. So solve the problem using theta sub s. Much easier to do because we know a lot about working with our trig functions for angles in standard position. And then at the very end, we're going to do a conversion back. At the very end, they're going to ask us to give us a bearing for what this resultant vector turns out to be. So at the end, you want to convert the angle back to a navigation bearing. Now, in general, I don't like an idea of doing a conversion to then convert back, but in this case here, I think it makes sense to do this because of the fact that all of the work we've done have been with angles in standard position, and our trig functions work very nicely with angles in standard position. One thing to note here about this calculation when you go to convert it back. When you go to convert it back, here's going to be your conversion. You'll take your angle that you come up with in standard position, and you're going to subtract that from 90. 90 minus theta sub s. And you have to normalize, or I'm going to use the word normalize it here. Normalize it meaning a bearing has to be an angle that's between 0 and 360. If you get something that's outside of that range, then you've got to find a coterminal angle to that angle in order to get it in the right range. So that's what the adding 360n does. Remember, that's how we defined what a coterminal angle was. If you have an angle theta, just add 360 times n, and you got a coterminal angle for any value of n. So that's what the plus 360n is doing. It's normalizing it to a bearing measurement that has to be between 0 and 360. Sometimes n will be 0. If your angle theta sub s there is between 0 and 90 degrees, then n will be 0. But if it's bigger than that, you'll find out that n is going to have to be equal to a positive 1, because otherwise you'll end up with a negative result here when you subtract from 90. So the key there is that make sure that when you're done, theta sub b is between 0 and 360. Okay? All right. Let's take a look at an example of navigation bearings and solve a problem using that. So look at example 5 here on 468, page 468. It says Victoria walks due south, that's a bearing of 180 degrees, and then turns and walks 40 meters along a bearing of 250 degrees. And the question is to find her resultant displacement vector from the starting point. All right, so the first thing you should do is try to draw a sketch of what they're describing there for us. So I'm going to do that. And I'm going to use kind of a little crosshair here to indicate your north, south, east, west. So I'm going to put that in, maybe we'll do that in a different color there. I'll put that in black. So that is my north, south, east, west marker there. That's my crosshair. So I've got a vector that's straight south. So this is 90 meters. It said that we walk straight south. Okay. And in fact, maybe I'll mark my angle here in the same color that they gave us, or my bearing, I should say, that they gave us was 180 degrees. Okay. So that's the bearing to go straight south. And then I'm going to put at the head of this vector a little crosshair here. Sometimes that's a nice way to think of this here as you sketch this. Draw your crosshair so that way when you go to measure your angle, you're measuring it correctly. It says that she walks 40 meters at a bearing of 250. So 250 from here is going to put me into this third quadrant of my sketch. I'm going to do that in a different color here, though. So 250 is going to be something about like this, and it's only 40 meters, so it's not as far. So we'll do that. And I'll mark the angle. The angle here is 250 degrees on a bearing of 250. All right, so then the resultant vector that we're looking at here is this vector right here. That vector right there. That's our resultant vector. And they called it R, so I'm going to go ahead and call it R as well. But for many of these, we've used V for vector. That's fine to do. All right, so that's the setup for this problem here. Okay, I'm going to take each of these vectors here that they've given us, and I'm going to write it in its component form. But again, I'm going to put it in standard position in terms of the angle. So when I go to write the angle here, I'm going to take the angle they gave us and subtract it from subtract it from 90 degrees. I'm writing actually the coterminal, the complementary angle to it. Okay, so let's do that. I'm going to do this in the same color here just so we're clear here. Let me call the vector that I've got there in red, I'm going to call that vector A. So vector A is equal to, its magnitude is 90, times the cosine of, maybe I'll actually write this as 90 minus the 180. Again, I'm writing that in the form of 90 minus 180. That's what we just talked about on the previous slide there. Times vector I. And I add that to 90 times the sine of 90 minus the 180 times vector j. So this is equal to, maybe I'll simplify that because I'm going to use this vector here a little later on. That's a negative 90 for the direction that I've got here. And it's certainly okay to write that the first time that way as well, but I want to make sure it's clear where we're getting that number from. Negative 90 is our direction. And now I'm going to do that same thing for vector, I'm going to call it B here, the one that I've got in blue. Vector B is equal to, the magnitude is 40 times the cosine of, and again it's going to be 90 minus the bearing that they've given me, which is 90 minus 250 times vector I, and then 40 sine of the 90 minus 250 times vector j. And again, you can just write that all simplified in the first step here, but I want to make sure it's clear where we're coming up with these numbers then. So it's 40 times the cosine, 90 minus the 250 is going to give us what? Negative 160 is what we're going to have here, times vector I, plus 40 times the sine of a negative 160 times vector j. All right, so we've got our two vectors there. Again, that's the first step, is write the two vectors they give you in component form, and then we can start finding her resultant displacement here. To find the resultant displacement, we're looking for vector r, and vector r is just the sum of those two. I've got these two vectors lined up head to tail, so since they're head to tail, I can just add them as is to find that vector r there. So I'm going to do this, let me just draw a line here. So vector r. Vector r is defined then as vector A plus vector B, right? That's how we're going to find that resultant. Sum those two guys up there. So let's take and sum those two up. And again, the way you sum those up is you take the I parts and add those together, and then you take the j parts and add those together. So that's what we're going to do. I've got 90 times the cosine of a negative 90 plus the 40 times the cosine of a negative 160. That right there is the I part to our vector. And we'll add on the j part. See if I can squeeze that in here. It's 90 times the sine of a negative 90. And then plus 40 times the sine of a negative 160. That's times vector j. All right, that's vector r. Let's actually find out what the components are there. So let's grab our calculator and evaluate this. Let me just get rid of this here. I could possibly reuse some of that, but I'm going to just start from scratch here just so I get the right equations in here. Let's take 90 times the cosine of a negative 90. And we're going to add on 40 times the cosine of a negative 160. And again, you should probably get the idea that we're going to reuse these numbers, so it's probably best if right away you store these. That's what I'm going to do again. So that's a negative 37.588, it looks like. And let's do that again, but now let's change a couple of things. I'm going to change this to y, and I'll change this to a sine, and that to a sine. You can retype the whole thing. Oh, well, maybe I should have retyped the whole thing. That's a 90, and then that's the sine. You can retype the whole thing or just fix a couple of things there in that previous calculation, and we got ourselves the y component there. So there's our horizontal and vertical components of our vector there. In fact, let me grab a picture of that, and we will put that into our slide here. All right, so let's rewrite these. So we've got the I part here is the negative 37.588 times vector I. And the y part of this is a minus 103.681, it looks like, 681, and that's times vector j. All right, so there is our vector that we're looking for. This is part A of this problem, by the way. Is coming up with the resultant vector. Now they wanted the resultant displacement vector though. So let's go ahead and find the actual magnitude and direction for this vector. Technically we have the vector here, but I want to go ahead and find the magnitude and direction as well. So we want to find the magnitude of vector r. Magnitude of vector r, well that's actually pretty easy to do at this point. I can just take the square root of these two components, negative 37.588 and the negative 103.681 squared. And again, this is why storing these on my calculator is pretty nice, because that makes this next calculation here pretty easy. Let's jump over to our calculator and crunch that actually. So we just want to find the square root of x squared plus the y squared. So we get 110.284, it looks like, 110.284. $110.284. And I think they gave us, did they give us units in this problem? They did, yeah, we're working in meters there, so we should put a set of units on that as well. 110.284. There we go. So that's the magnitude of our vector. Now let's go ahead and find the direction of that vector. Now, again, they gave us this problem in bearings. My answer should be in bearings as well. So I'm going to find the direction of my vector in standard position, and then we'll convert that over to a bearing measurement. All right, so I'm going to call this theta sub s, like we said to do. Just help me remember that this is not the angle that I'm looking for. This will just help me get there. So theta sub s, remember you can calculate the angle there by just taking the tangent inverse of the negative 103.681 and divide it by the negative 37.588. And we're going to add on 180n. Now think about what quadrant this shows up in. Negative 37 means you're going back to the left from the origin. Negative 103, that means you're going down. That puts you in quadrant 3. So since we're in quadrant 3, we're going to have to make n equal to 1 to get an angle that's in the third quadrant there. All right, so let's calculate that as well. Again, I've already stored this on my calculator, so that makes this calculation real easy to do. Tangent inverse of the y over the x. And again, this time I'm adding the 180 on there because I want to be in the third quadrant. And we end up with the 250.073, it looks like. Let me go ahead and grab a picture of that. All right, so we have theta sub s. Our angle, our direction there from standard position was equal to 250.073 degrees. But again, that's not the question. The question is what's the bearing measurement, because that's the standard they were using there for this problem, or that's how they measured their angles for this problem. So remember, to calculate your bearing measurement, you just go back and take your standard position angle and subtract it from 90 degrees. So it's 90 minus theta sub s. And you have to find a coterminal angle to that, or you potentially do, to make sure that you get an angle that's between 0 and 360. Bearings have to be between 0 and 360. So since theta sub s is 250, when I take the 90 and I subtract off the 250, I'm going to get a negative number. So I have to make our n equal to 1 in order to add on 360 so I get an answer that's positive. That's what I'm looking for. So let's grab our calculator and do that. So again, the calculation is just 90. Maybe I should have stored that angle there in the previous step here, but that's all right. I think I can just grab its value here. So 90 minus that value. I'll just use answer here to do that. And then I have to add 360 so I get a positive answer here. Otherwise, I'll get a negative result. So 199.927. In fact, that's the screenshot that I really should have here. Let's grab that one. I'll get rid of this one. All right, so there is our direction for this vector, our bearing for this vector. This is equal to 199.927 degrees. There is our bearing. All right, that was part A. Part A had quite a bit to it. If you look at part B says, what is the starting point's bearing from the place where she stops? So, in other words, if we go back to our picture here, she stopped at this point right here. So they're saying if you were to try to start at the ending point and go back to the original, in other words, we're flipping this vector around. What if we wanted to do that instead? And the question they're really asking us is if you put your little crosshair here again, measure the angle of this vector right here. What's that bearing? Okay. What's that angle? Maybe I'll call it theta. Well, it's a vector that's in the opposite direction. So let me call it theta sub O maybe for opposites. But we're headed in the opposite direction there. Well, the nice thing about that is finding vectors that are in opposite directions is pretty straightforward. So for part B, if you want a vector that's in the opposite direction, I'm going to call it theta sub O, that if you just add, well, maybe I should write this first. If you have two vectors, theta, if you have two vectors that are in opposite directions, then it turns out that theta and theta plus 180 degrees are in opposite directions. So adding 180 onto your vector gets you in the opposite direction. So the cool thing there then, to find out this vector, we'll call it theta sub O that's in the opposite direction. If I just take my bearing that I came up with, theta sub B, and I add 180 onto that, and again, I have to normalize this. Anytime I'm working with bearings, I got to make sure I add on this 360 n to get an angle that's in in the range from 0 to 360. So if I add 180 to the 199, I'm going to get an answer that's more than 360, aren't I? So I'm going to have to make n equal to -1 here to make that happen. And so what do we end up with? Well, actually, that we could probably do without our calculator, but we can run that through the calculator here. So if I take that answer there, and I add on 180, but then I have to subtract 360 to get it back in the right window there, 19.927 is the value that we come up with, 19.927. All right. That right there is the second half here of section 9-6.